Hi everyone, I'm Arturo Esa, and today I'm going to be speaking about hierarchy compositional tasks and deep CNNs, and this is joint work with Annie Bambursky, Shani Liao, and Tommaso Poggio at MIT. Now, perhaps the best paraphrasation of this title could have been why and for which tasks do CNNs perform better than fully connected networks? And a fully connected network is a network that can essentially perform and compute a global and non-compositional task given its network constraint and architectures. A CNN is a network that can compute a local and compositional task. And a deep convolutional network is a network that can compute a local and hierarchically compositional task, once again, given its network constraints and architectures. Now, what does this mean in the real world and when we're talking about images? Suppose we have an image and we want to compute its average color. It seems like the shallow fully connected network would do this task better than the other two. If we want to compute its texture, that is going to rely on localized second order image statistics, it seems like a CNN would do better and a really good job. And it seems like for the object recognition task, which is essentially extracting what the percept and the class is, which is going to rely on integrating features over some sort of visual hierarchy, it seems like the deep CNN would do this task better than the other two models. Not that the other two models can't do the task, by the way. But how do we actually test this, right? We're gonna have to do some sort of funny business because the network architectures are essentially immutable properties and they can only change as you train them and rely on SGD. So we can't change the network architectures. What we can change is the input image distribution. So we're going to train and test on images where we've disrupted the locality prior by scrambling them. And in fact, we're going to engage in varying the degree of scrambling, whether it's a top-down scrambling where we preserve the fine details but disrupt the coarse information, or the other way around in bottom-up hierarchical scrambling. And we're also going to briefly mention how these results look like when we train these networks on these type of image distributions, when we train them on the unscrambled images and test them on the scrambled images, again, as we vary the degree of scrambling. So more precisely, let's kind of go back to our projections and our predictions for the experiment. For the object recognition class, which is a classification task, we think that the deep CNN is going to do exponentially better than the fully connected network when the locality prior is still there and is not disrupted. We project that for the texture perception class, the deep CNN is going to do better than the fully connected network, but only mildly, just by a bit. And finally, we think that counterintuitively, perhaps the shallow fully connected network is going to estimate color, which is a regression problem essentially, better than the deep CNN. Well, these are our three predictions. Now let's look at the results. For the object recognition task, if we have our first VGG11, which is going to be our deep ConvNet model, we see that essentially when the image has been unscrambled, the network does really well. But when it's tested on scrambled images, the performance drops or decays really, really fast. But when it's trained and tested on the same type of distribution, the performance still decays, but not as fast, surprisingly, as for the control condition. But now let's look at how other systems, such as a fully connected network, would perform on this task. Naturally, it's not affected by scrambling because it doesn't have any sort of locality priors, but it does not do as well as the BGG11. In fact, it does not do as well even as you make it wider and match a number of parameters or make it deeper as well. And perhaps more interesting is that if we have a heavily underparameterized convolutional network with only 3 layers and 6,000 parameters, it can do just as well as the overparameterized fully connected networks in the unscrambled condition. This pattern of results doesn't change if we do bottom-up hierarchical scrambling, by the way. And what's also interesting is that we find these Gabor-like oriented filters emerge only when the images are unscrambled, but not when they're scrambled, matching the theory. Now, many people can ask questions about the texture bias. Do these results hold? Do they change? Yes, no, why? What we did is we repeated the experiments on style transferred CFAR10 images, and we find the exact same pattern of results, but now the underparameterized 3-layer ConvNet is doing better than the fully connected networks, which is a pretty interesting result. In general, the magnitudes of the accuracy also decrease, but the pattern stays the same. And we also see that these Gabor-like oriented filters stay only for the unscrambled condition for the convolutional networks. Now, for the texture perception class, which is going to rely once again on localized second-order image statistics, we find very interestingly that all the network curves for the accuracy and the performance stays the same. They're flat. They don't change as you scramble the image, which is expected for the fully connected networks, but also somewhat expected for the convolutional networks too. Perhaps the counterintuitive result here is that now the underparameterized 3-layer ConvNet is doing better than the VGG11. And once again, we see these type of cosine functions emerge only for the unscrambled images compared to the scrambled images. Finally, last but not least, but probably one of the most interesting results is the color estimation task, where here lower is better because we're computing the aggregate mean square error of what is the average color of the image. We find that for this task, it's actually the fully connected networks that are doing better exponentially than the convolutional networks. And what's also very interesting is that the filter structure looks nothing like oriented Gabor's. And this actually makes sense if you think about it, because the convolutional networks have to compute an average of an average of an average of an average of the pixel intensities to finally come up with the average pixel intensity value to compute its color. So it doesn't even need to compute any sort of edge detection mechanism. This is very interesting. So what have we learned so far? We've learned that CNNs are amazing only when they can exploit the local image structure of images and their compositional nature given the task for the object classification problem, for example. We've also found that deeper is not always better, and that receptive field size matter because the 3ConvNet has a bigger receptive field size actually than the VGG11. It's 5 and not 3. And finally, we found that the fully connected networks can approximate global and non-compositional tasks better than the deep CNNs. And once again, this is due to the proper match between the approximation function and the actual network architecture that can make it more realizable and learnable via SGD. For more information, please check out our preprint online. That'll be all for today, folks, and I'll see you all next time. Thank you for your time.